Okay. For the case of those guys who were not here last week, my name is Charles Suwazafani Msipa, and this today I'm presenting derivatives of, I said derivative there, it's supposed to be derivatives of inverse trigonometric functions and hyperbolic functions. That's basically what I'm going to talk about today. But I was going to start from where we left the other day, the revision we did. I just want to highlight something there. So after the revision we did, which is on that video which I just shown you, I think you need to have a summary of this nature. You know, this is a table of derivatives, and these are the derivatives which I was saying to myself, standard derivatives. Everybody must know that the derivative of sec is sec tan, the derivative of sine is cos, but like what we agreed that they said, well, it doesn't matter what argument, every time you differentiate the function, you must multiply by the derivative argument. That's why we have that u dx there, du dx there. But to understand that, what is this du dx, I think you need to discuss this first of all. Let's suppose we're given a function, and this function y is a composite function. Actually, it depends on u, and the u depends on x. So to compute a derivative of such kind of function, you would say, since y in the final analysis depends on x, so the derivative will be denoted as dy dx. Now to get this derivative, you would call upon the derivative of y, which is the immediate function there. Then you say dy, in this case it will be y, which depends on u. And then that will be multiplied by the derivative of u, and you can see there, u depends on x, then you say du dx. That is expressing exactly what I said the other day, that the derivative function, you call upon the immediate derivative of the function, and you must always multiply by the derivative argument. And then you can see here, if we were to follow about the derivative argument of u here, you would basically multiply this thing by dx, which you normally don't write, because that's the simplest derivative there. This simplifies to 1. So we just leave it there. Altogether. So an example of that is something like this. Let's say you have y equals 2 sine of x squared. It simply means that our u here is x squared. So if we're going to differentiate y is sine. This thing says y equals sine. So y is sine. So which means we have got to call upon the derivative of sine, which will, sine will become what? Cos as a derivative. And then we retain the argument, in order to retain the same argument, and then we multiply it by this, the derivative argument, in this case, which is going to be 2x to the power 2 minus 1. I'm just emphasizing there that, remember here, we are applying the power rule. Am I making myself clear there? Okay. So then after mastering this theory, actually, I don't know how I can emphasize this thing. There's no way you can go to a class for integration or differentiation or applications of differentiation without knowing all these derivatives. You must know them. That's specifically. So that's the thing. So after mastering all the derivatives, you know them, then it's important also to master the rules of differentiation. This is the one which I've just said there. Derivative of y equal to u multiplied by derivative argument, given y like that. And then you've got product rule. What is happening here, of course, for these functions, you can just use prime to indicate the derivative of the function. So now, if you've got a derivative of a product, then you can use the product rule that way. And then the quotient, you can use the quotient rule this way. Be careful with the quotient. The product of two numbers, 2 times 3 is equal to 3 times 2. But the 2 divided by 3 is not equal to 3 divided by 2. So what am I saying there? Is that when you are dealing with division, you must be very, very careful of the order. Whether you are multiplying numbers or you are differentiating, you are applying product rule there. It's very important that you apply the rule very accurately. The order is very, very important. Am I making myself clear, guys? Okay. Then the next thing is, I said today we are going to look at the derivatives of inverse trigonometric functions and the hyperbolic functions. There it is. So in this case here, we are talking about more or less something like this: sine second function x when the argument is just a simple x. But it could be something like this: sine second function of u of x, like we've done there. But sometimes you can just write u like that. And in some cases, some people can just use that sine second function of another function of x, which is exactly expressing the same thing. So that is the case of hyperbolic trigonometric function, and then the case of hyperbolic functions is similar. So what I want you to do now, before we look at the tables of these derivatives, I want to discuss one of, like this, I'll take one, the trigonometric, inverse trigonometric function, and just work throughout it with you, discuss it, so that you just understand how this formula you see on the tables come about, not take them as just absurd, empty things which are not thought out very clearly. So let's do it this way. Let's suppose with the function y equals to second function of sine of u. I'll just say u there. Everybody must understand that it's a u of x. Altogether. Okay. So now if we are tasked with finding dy dx, we are actually implying that this function in the final analysis depends on x. Then this is what you are tasked to do. At this stage, when you come to do this, I don't know how to do it in next one, but normally I would come to talk about this when you know the chain rule, maybe all the basic derivatives, and you know what we call implicit differentiation. So I'm going to, here now in this discussion, combine the use of chain rule, implicit differentiation, to try to get the derivative of this function. Okay. Please, if I say something which, or a word which you don't understand, please say so. Like I told you yesterday, I'm not an English speaker. I just communicate a bit in English. So if anything is sounding strange to you, you must stop me and say, what do you mean by this? Altogether. But I guess you are going to be able to guess what I'm trying to mean, because you are a bunch of educated people using the language of Figure and Balula. The punch, always a punch, a punch. Okay. So let's go. What I'm going to do now. First, I want to remind you this. If you've got a function, f, and is cascaded with its inverse, and its inverse is acting on something like an argument x, this is the same thing as cascading, first applying the inverse, and then applying the function, and the function acting on s, and this will give you something. What's going to give you? What is it going to give you? Nothing. Okay. What about if you've got ln and the e of x, which is the same thing as e ln of x? What is it going to give you? Huh? X, you crammed that one without understanding. You crammed that one without understanding. Why is it giving me x? Come again? Because it's a function in this inverse, isn't it? So a function applied to the composed with this inverse like this will always give us the identity. Now it gives us back identical what we picked there. We pick the x there, we cascade that with the we get that. Altogether. That is called composition of function with its inverse is the identity. So you must know that principle, because if you don't know that, what I'm going to do next now is going to look like Greek or something which you've never seen before. It's based on this thing. So what happens here now? If, first of all, remember in next one, you could get the derivatives of functions like this using the first principles and using the limit. Altogether, you don't try to do this thing. I've never tried to do it myself here, that kind of a thing. With this kind of function, I've never tried to do it. And I don't remember any lecturer of mine discussing this using first principle. All that means is tedious and difficult to do. And normal human beings, when they see something difficult, they'll find an easy way of doing it. That's natural. That's natural. Human beings, they find something difficult, they will always find an easy way of doing it. Altogether. Traveling was difficult by foot. What did they do? They invent wheels, they invent cars, they invent everything. Or if you don't know that, then you're too young to be here. Okay. Alright, so what happens now? We can apply sine on both sides of this. We say sine of y equals to sine of sine second function of u. If you look at what I'm doing here, I'm doing exactly this. This is expressing for any function with its inverse. This will happen. So now this is sine and its inverse. The same thing will happen. So this is going to be u. Are we following, guys, the logic? Are we following? If you're left behind, please shout. Tell me what you don't understand. Right. Now, when we come here now, we can now just focus on sine of y and u. Then once we've done that, now what we can do, we can now try to differentiate the equation with respect to x. Why am I differentiating the equation to x? Because I'm actually looking for dy dx. But if I think of the chain rule here, derivative of sine multiplied by derivative argument, the derivative argument will actually dy dx altogether. That's why I'm doing that. So I will differentiate both sides of this equation. Sine y equals to u. I'm differentiating like that both sides. Then when I do that, the derivative of sine will be cosine. Retain the argument multiplied by the derivative of the argument. Then when I get this side is a u, which is a u of x, I will just get I think my u there more or less looks like y. Du dx. Are we all there? Okay. So now I think you can see now that we are closer to getting to what we want. What we want is dy dx. So we can just solve this equation and make dy dx substitute formula. Then with that we do it by dividing both sides by cos. But dividing by 2 is same as multiplying by half. Is that true? So dividing by cos is same as multiplying by 1 over cos y. Do you agree on that one? So then if you do that, then we're going to have here dy dx equals to 1 over cos y multiplied by the derivative of the argument. I would like to use that derivative of the argument multiplied by derivative of argument, so that people never forget that when you differentiate, there will be always multiplication by the derivative of the argument. Now, this is sine y, altogether. But you see, our function y was given in terms of x, but this derivative is coming in terms of y. I think we must find a way of getting back to x, or u at least. There's no u here. The function here was given in terms of u, and here we got y. So we need to go back to y. But what is u? U is this. Do you see that? U is that. But first of all, before we do that, let's think about this. Let's think about sine squared y plus cos squared y, and I'm expecting you to tell me what that is equal to. Is equals to 1. And I think we can see here, we can make cos y substitute formula. If you make cos y substitute formula, we're going to give you cos y equals to square root of 1 minus sine what? Sine y squared. Is it? Is that right? Okay, so that is that. So which means now this derivative, we can write it in terms of this. Let's go back there and say dy dx is equals to 1 over cosine. Cosine is that. Then you just write the 1 over 1 minus sine squared y multiplied by the derivative of the argument. Do you agree there? Now, we are now closer to getting the derivative exactly the way we want it, because now we've got sine here, and the sine is actually u. There, sine is u. The function was given as a function of u. The derivative must come as a function of u also, isn't it? So now what we can do now, we can do this. We can now rewrite this as 1 over 1 minus 1 minus the argument squared, because use the argument is minus the argument squared multiplied by the derivative of the argument. So guys, this last formula here, which you have here, this last formula right here, you must be able to read it to yourself. Read it to yourself. The function which was given was y equals to sine second function u. What does this say? It's saying the derivative of this kind of function is just simple 1 over the square root of 1 minus the argument squared multiplied by the derivative of the argument. Are we getting that clear? So now let's try to see whether we can apply this thing to a situation like this. We've got y equals to sine second function square root of x. So you see now our u is the square root of x. So now if we were to follow this, formula there, we will say the derivative of this is remember this comes from trigonometry altogether. Okay, so 1 over the square root of 1 minus u. What is u? Square root. So we say square root there, square root of x all squared multiplied by the derivative of the argument. I'm putting it very clear so that you can understand how I'm applying the formula accurate. Yes? Come again? I don't cut 30%. Can you speak louder, please? This with x. I'm giving you a function. This is a function. This here up to there, we're discussing a general formula for any u. Do you understand me? We're discussing the general formula for any u. Now from here, I'm giving you an example whereby I'm taking a function where u is the square root of x. You don't need to understand that thing. You just have to accept the function I'm giving you, then work it according to that formula. All together? Yeah. Now I'm applying that formula as it is. What you should do now, monitor what I'm doing here and see whether it is in agreement with what is said there. So I'm seeing it exactly. There is the argument u. This thing is saying 1 over 1 minus the argument squared. There is the argument squared. There it says multiplied by the derivative of u, and there is the prime of u. Clear now? Okay. So now what we're going to do now, we need to carry out this kind of differentiation now. There is just rearranging the formula according to the formula, and the differentiation just goes there. But the radical sign like this is power half. So I'm going to repeat this 1 over 1 minus x. If anything is surprising you, you must tell me. What is surprising? Nothing. Okay? Multiplied by half x half minus 1. What are we doing there? Applying the power rule. Altogether. Okay? Then let's simplify that. I think if we simplify that, we're going to have 1 over 1 minus x. Can somebody tell me why do we have x there? Come again? Come again? Square, x is the square of square root of x. X is the square of the square root of x. Yes or no? Okay. So then, x is the square of the square root of x. So you square the square root of x there, you must get x. Then here, we're going to have x to the power minus half. Can we do further simplification? What should I write here? What should I write? 1 over, let me write this here, 1 minus x. What else should I write? 2 root x. That is correct, I think. If you are surprised, tell us. Because in the absence of knowledge, anything is surprising. Even the rain used to surprise primitive people. Are we there, guys? Okay. So now I'm going to ask you to do this one for yourselves. Let's say y is equal to sine sine that 3x plus cosine second function x over 2. But before we do that part there, I think is the time now I can show you the table of the derivatives of these inverse trigonometric functions, so that you can we cannot have time to derive each and every formula altogether. But this one which you've done must give you an idea of what are the principles, what things you should apply in order to get to those derivatives. Is that right? Okay. Let me show you the tables of these derivatives. Right. After discussing the derivation of this formula, I think it's time to look at the whole table of these derivatives, and then you can actually learn them and just try to see what is the pattern followed there. For example, look at this one and this one, these two. Remember, in trigonometry, the derivative of cosine is minus sine. and the derivative of sine is cosine. But when you come here, is the derivative of cos second function, which comes with a minus sign. I think you notice what I'm saying there. When you've got this there, is actually the same thing as what we've just seen, that this is equals to 1 over square root of 1 minus the argument squared multiplied by the derivative of the argument. But when you write it as a fraction like that, then this can appear there as a numerator altogether. So don't get confused about that. So these are the table, this is the table of derivatives, which now, the example which I was just trying to give you now, you can apply this to get the derivative of what I've just given you. So now, let's go back there and get the derivative of this function. Can you now compute the derivative of this function? I think you've got that table in your notebooks. I think it's page 11 or so. So can you get that derivative? I will ask one guy to give me the derivative. I hope I've given enough time to attempt the exercise, at least to, maybe even if you're not able to do it, but to recognize what is your difficulty. So let's just try to do this one together. So what will happen now, because I remember these things, I'll just do it very quickly. dy dx, I've got to differentiate there and a differentiate there, altogether. So I'm going to write it slowly as this one. I know it as 1 over the square root of 1 minus the argument. Is that correct? Argument squared. Good. Squared multiplied by 3x derivative of altogether. Okay? Plus here minus 1. Maybe let's put this in brackets. Minus 1 over square root of 1 minus x over 2 squared multiplied by x over 2. For fast learners, I'm doing this thing too slow, but I normally teach for slow learners because I'm also a slow learner. All together? Okay. So that's the thing. So at that point now, we can continue to differentiate that, square that. If we differentiate, we're going to get 3. Then multiplying by 3 over 1, we're going to get 3 over square root of 1 minus 9 x squared. And the differentiating there, I think we get half. So we're going to have 2 fractions then multiplying each other. Then we're going to have minus 1 over 2 square root of 1 minus x squared all over 4. All together. Then we'll be done with that kind of example. I think so. Let's see if I have this. The answer in the book is different. Some bit of homework which I'm going to give you is, I think it should be worthwhile for you to try to do the similar kind of derivation with cos and sine and tan. Not for any purpose that I'm going to ask you to do it, but that experience will make that thing actually be consolidated in your system, and then you get used to it. Then again, remember, hyperbolic functions also got identities. So you can use identities similarly. You can use it following exactly the same principles. You can use identities to derive these ones, and then apply them just like we've done on that example there. How do you guys? Okay. So now, I think at this stage now, I will turn to your notebook and try to show you where these things are coming from, then show you which practice you must carry on doing. Otherwise, for now, I would like to say thank you for listening.